been a really long time. The new macOS video seems to be doing really well for some reason, and it occurred to me I hadn't made a video in like a year, so I thought I'll fix that. We're going to jump straight into the topic of today's video because I'm very excited about it, and I think you will be too. Before I go on, I'd like to point out that a lot of people said that I was mispronouncing the title of macOS X, and while you're probably objectively correct, I'd like to say a lot of the people in my life, even the big Apple fans growing up, called it macOS X, which has led me to believe that it's likely a regional dialect. And if that is the case, then I'm going to continue to say it this way because I'm proud of the little middle of nowhere I come from. Anyway, without further ado, let's get going. So, because I love you, I decided to get a whiteboard because it would be easier to see. I got it a year ago and have been expecting to use it, and I have not. So it's just been sitting in my middle of my room waiting for y'all this whole time. Anyway, we've already kind of gone over this, but it'd be nice to have a refresher and maybe a couple of corrections from my last video before we move into the bash script that I'm going to walk y'all through. First off, how exactly does Linux work? And I don't mean the more complex elements. I mean, like, how does the kernel work? Well, one thing you have to understand is that your RAM on your computer is where your operating system lives, but it is incredibly reliant on your disks. Back in the 80s, we didn't have hard drives. I say we as if I was around. I was born in '99. People didn't have hard drives by default. They had to load things from floppy disks. But you'd be surprised how many principles have remained the same. So the first thing your computer does is it loads a bootloader. UEFI is the more modern bootloader. In my last video I was talking a little more about traditional boot, but UEFI is the newer standard. But regardless, you have to boot. And so your BIOS takes a look at your disks, which may be your inserted USB thumb drives, it may be a physical optical CD you have in your machine. Obviously it may be your hard drive, but regardless it looks for a bootloader. Grub is a very common one. Systemd boot is also a very common one in the Linux space, while Windows uses what's called Windows Boot Manager. Now what this does is its job is to pre-populate your RAM so that your operating system can get going, load files in on its own eventually, and then down the line load proper applications from your disk and let you do what you want. So the very first thing it loads is the kernel. This is a single binary, so just like a single program, right, that it loads into memory, whose job is to load everything else into memory. Now the Linux kernel, just like any other program, can accept arguments. These are little pieces of text that specify what exactly the Linux kernel is going to do. It sets options ahead of time. This is very similar to when you open a program with a particular file in mind. Like if you double click a text file and it opens up Notepad with that file, you've passed in that file as an argument. We're actually going to get into a couple of arguments later on because they're going to be very important. But with that said, the next thing that it does is it loads in the initial RAM file system, or init RAM FS. We're going to be creating an init RAM FS, and I'll go through those details. But the idea is that the kernel is a single binary, and you are setting up the initial file system that it's going to be loading everything else in from. Now, with a traditional Linux from scratch approach, there are many GNU utilities you have to individually build and then place in your initial, like your init RAM file system, in order to be able to do things like see the console or list files in a directory. But for simplicity's sake, and because I personally like it very much, we're going to be using Busybox. Now Busybox is a single binary, just a single binary, that creates a set of links so that you can use your computer as if you have all of these GNU utilities installed, but it's really only one program. And it makes it very easy to get started with a project like this. Now another thing that Busybox does is it itself has a program that it launches as an initializer. So it's got its own initialization binary. Let's go down this list a little bit. So Grub loads in Linux. Linux loads in Busybox. and then Busybox runs this initialization program. On a more complex system, what would likely be happening here is that you would load in systemd, or you would load in OpenRC like Alpine Linux does. These are called your PID 0 functions because they have a process ID of 0. And if they ever stop, you get a kernel halt. But your computer just stops working. Like if this program ever goes down, your computer is toast. Now with that said, once this is done, from there, on a typical computing system, it'll allow you to then load other apps and files into your RAM from your hard disk. But the idea is that these themselves, when we're working on them, are essentially like just two files. This right here is your binary. It's just it doesn't have a kernel extension. It's just BZ image, and then it's a bunch of ones and zeros in a file. And this is actually a .ing image that is then opened up and populates your system. This might not make a lot of sense right now, but when we're walking through the bash script, I swear, this should make a little bit more sense to you. So what exactly is this bash script going to do? Well, the bash script that I've set up should be every step that you need in order to download the source code for all of the tools we need to build a functioning system, do all the customization, and then build it. And at the end, we have a QEMU line. A QEMU is an emulator, and its job is to build a little virtual system so that we can play around with this new Linux distro that we made. And as a freebie, at the end, I'm going to show you how to create a CD image out of this distro we're making that you can then actually put onto a thumb drive and then boot onto a computer. So if you want to run this system on real hardware. It won't install the system, but it will boot from the drive. Trust me, installation is it's a whole other animal. Anyway, so first things first, we got a bash script here. We're announcing that's what this is from this commented line. The next one, set tacky. Make sure that the script itself is tacky, just like that joke I tried to make. No, but seriously, set tacky lets the script know that if there's an error, to just cancel. You're going to see a couple of times where it's going to ask you for your super user permission, but you can trust me, I swear, I'm very trustworthy. We're also going to be walking through this, so I'm going to be explaining what each of these lines does, so you can feel a little bit better about that. So this is designed to work on Debian-based Linux distributions like Ubuntu, Pop! OS, what's that other one that's really big? Linux Mint. There we go, Linux Mint. This is really the only part you would change if you were on Arch or Fedora. But you would basically just change apt to whatever package manager you're currently using. Apt is what Debian-based systems use. These should be all the packages you need to build everything that I'm going to walk you through later. Let's go down here. I am cloning, not from the original Git repo. I know I might get some flack for that. I just liked how clean these links looked when I used the mirrors. But you can change this if you want. If you want to use the official GNU repository, no one is stopping you. You can go crazy. Or if you want to use an older version of Linux, you can do that too. Regardless, what these do is these pull the source code for these three applications and then put them into folders within this folder that have the name Linux, glibc, and Busybox. If you decide to pull your own source code or whatever, just make sure that they have these names or the script will break. Now, this is obviously designed to run multiple times because you probably don't have an init ram fs file or folder. However, what we're going to want to do is we're going to want to create a folder that will represent the initial RAM file system. At the end of the script, we're going to be compressing this into a .img file that we can then pass to QEMU, and what it's going to do is it's going to unravel it and load that into RAM. And then from there, you'll have Busybox, and you'll be able to download other programs and run them. And we'll have some fun with that a little bit later. We've got a lot of files, or a lot of folders here. We have proc. This represents all of your processes that are running. a lot of these have system utilities because everything is a file in Linux, or at least it's designed to be. A lot of these aren't necessarily even, quote, real folders. They just exist so that the Linux kernel can communicate with other programs. So we have a universal interface for understanding what's happening on the computer. Now, first step, compiling the Linux kernel. This is real easy. Now, make files are amazing. They allow you to configure all sorts of different flags before you turn your source code into a binary and can run it. Now, def config, just make sure that the defaults are set. But if you want to, you can actually type in, and it would look like make menu config, and this will open up a little menu, and you can go through and customize all sorts of things. Now, for most people, there isn't much of a reason to do this, but if you want to performance tweak, if you want to include or not include certain drivers, be my guest. You can go crazy with that. Finally, we got this. So we're telling Make that we want to build this BC image binary, and we're telling it this line right here means I want to use all of the available cores on my computer to do this. nproc just returns how many cores your CPU has. Like if I run it here, it's telling me I have 12 cores. And then tacj just means, obviously, this is how many cores I want to use. Now, after that's done, you will have built a BZ image file. And we're going to want to navigate back out of that Linux directory. Now, what is glibc and why are we compiling it? Technically, if you want to, you can compile a functioning system with nothing but Linux and Busybox. However, you have to make sure that the static flag is set on Busybox, and most Linux software you will not be able to run. However, with glibc, you would be surprised that the majority of Linux software would now be able to run in your system. What exactly is this for? Well, so when I want to create a new, let's just say I'm going to create a new C program. So I'm going to do include sdo.h, main, return 0, and then printf hello. So this is an extremely simple hello world program. It's so simple it doesn't even have the world in it. But you'd be surprised how complex this is in assembly. And when you compile this program for different computer architectures, the assembly looks completely different. In fact, if you compile this for the same architecture on different operating systems, the binary that it produces will look nothing alike. The reason for that is that every operating system has a different set of system calls for putting text on the screen. And printf obfuscates, I cannot talk, I'm so tired, guys, obfuscates that. Now, how does it know to do that? Well, include is technically not a C command. It is a C preprocessor command. The idea is that it finds whatever this header file is, sdo.h, stands for standard input output, and it literally tacks on that source code to the beginning of your program. And then GCC, or whatever compiler you decide to use, takes that and turns it into assembly. Now, if we don't have a C library on our system, then we don't have this. This is one of the header files that comes with a C standard library system. Now, there are lots of C standard library systems. Some are big, some are small. Alpine Linux, my beloved, doesn't actually use glibc. It uses Muscle, which is less compatible, and in some applications is actually slower. But it does conform to modern C standards pretty well, and it's very small in size. However, glibc and Muscle should both be able to compile a program like this, and the output look identical. But that's why we want to include glibc into our little operating system that we're building, because we want to make something that's actually functional. This system will be able to run, even though it's very, very, very small, it'll be able to run quite a few Linux applications right out of the gate. In fact, I actually have a surprise for you, and if you stay to the end of the video, I promise you'll appreciate it. So, we go into glibc, we create a directory, titled build. Let's go into the build directory. Next, what we're going to do is we're going to run the configure file, and we're going to let it know that we want to set our prefix to /usr, and then we're going to make the program same way as before. Finally, what we want to do, and this is very, very important, guys. I've actually bricked a Linux system because I did not do this correctly. We want to make sure that our destination directory is set to the local build folder. If you don't do this, it will make glibc and then place it into your default Linux directory and overwrite your Linux system's existing glibc, which will cause all the programs that are built against it to crash, which includes everything. I mean, literally everything on your system. Almost everything ties back to whatever your C library is. It makes your system unusable. So you really, really, really want to make sure you have this line, I swear. So then we're going to navigate back up to our home directory. And then finally, Busybox. So we make the default configuration file, right? We make the Busybox the exact same way as we've made all the other programs to date. And then we run the make install command. And what this is going to do is this is going to place the Busybox binaries into a local folder that we're then going to copy the binary out of and then put it into our init.ram file system. Speak of the devil, that is exactly what we're doing in this line. See, I'm copying to my init.ram fs folder. First thing we want to do is we want to move the library files from glibc into the init.ram file system so that any programs that link against it will be able to find it. And next we want to move the files from Busybox, the install folder, into the init.ram file system as well. Let's go down a little bit. So we're going to make a bunch of, we got the evil number here, we're going to make a bunch of files and set the permissions correctly. The system is going to use these later on as it's setting up a console so that you're going to be able to have your console output appear correctly. Next up, these are actually important to glibc. What we're doing here is we are creating links between the lib64 folder where it wants to put the glib files and the lib folder within your init.ram file system where it expects them to be found. Without these, by the way, anything that links against glibc, which includes Busybox, will not run. Let's move on a little bit. Okay, we're going to create the initialization script. So remember how I said Busybox loads a binary named init? Well, the job of that binary is to load a shell script. This shell script is also called init. It's going to exist at the parent of your init.ram file system, and it's going to be basically everything you need to get started. First up, we're going to mount these three folders. Like I mentioned, Linux makes everything into a file, even things that aren't files. So we're explicitly telling your file system that the folder that represents the running processes is the /proc folder. Same thing with system file system and /sys, and the dev temp file system and /dev, which is where you're going to find hard drives and other hardware peripherals. Now, I'm calling my system AshDOS. The reason why I'm calling it that is because Ash is the name of the shell that is built into Busybox, and DOS obviously stands for disk operating system. So it's the Busybox Ash disk operating system. Now, this is also just going to put the date on the screen, and then this is going to tell me how much RAM we have, which you'll be shocked at how little RAM this actually uses once we get into that. But this is just a set of initialization messages. Now from here, this is a little hack so that when I start another shell script, it allows us to be able to create background processes, because without this line, it wouldn't actually do that. Finally, I initialize a second shell. Now we can type commands. And the moment that shell is done, it's designed to power off the machine. This line doesn't actually technically work. It still kernel panics. But regardless, the line is there. So what are you going to do about it? Finally, we want to make sure that the permission of the initial script we're running is given the execute bit. Otherwise, it will try to run it. It won't have the bit. It'll just fail. This right here, by the way, you don't really need this, but this is a little bit that sets the DNS servers. I've set them to the Cisco safe servers. And so if you ever do connect to the internet using ifconfig, which is built into Busybox, you'll have DNS. Now, what do we got? This is kind of fun. So Busybox actually comes with the Debian package. I'm not going to say binary because it's part of Busybox, but you can run the dpkg command. Now, what this is on Debian systems is it allows you to take .deb files and install them. Now, this is not APT. APT is a tool that sits on top of dpackage. So we're not able to search packages. We can't just do like apt install Python. You have to have an individual package, and if it has any kind of dependency, you have to make sure that you manually know what those are and install them first. But I figure for a minimal system, and since it comes by default, I might as well set it up. So I'm actually manually setting the libc package. I'm not installing it using dpackage. What I'm doing is I'm telling the system that it's already there. The reason for this is because it is. We spent all that time earlier packaging glibc, and I want programs that are installed from dpackage to know that I have glibc installed, so it doesn't complain about it. So that's what that is. Now finally, we cd into the initram file system folder, and we run this command. And what this does is it takes all the files and it puts them together in a .img file that it stores in the parent directory, which we then cd back into. This is actually something I filmed probably 45 minutes after I shot this part. You're going to want to do this. And this is going to be in the GitHub script, by the way. But what we're doing here is it builds the file like deep down into this folder, and you want to copy it up to your home directory so that you will be able to load from it pretty easily. All the examples after this use this technique. So I'm sorry about that. Anyway, future me over. Let's get back to what we were doing here earlier. Now finally, I'm going to scroll so you can actually see this. It's not like my head's in front of it. This is the QEMU command we use to test our system. You don't need this to build it, but it is very useful to test. We're going to specify that we have 2 gigabytes of RAM. We're going to specify the kernel file as our little binary we set up. We're going to set up that our initialization file system is the IMG we just made. Here are the aforementioned kernel arguments. We're going to be telling it that we're using a serial connection, which means that we're going to be able to see our kernel output in our terminal instead of having to open up a little like virtual machine window. I'm letting it know that the initialization program is this little script I wrote. I'm telling it to be quiet. I'm also telling it that I only want to see errors. Now I'm telling it, you don't actually, I'm going to go ahead and remove this and then talk about it later. You can actually pass a hard drive image to QEMU so that if you want to mount a hard drive, you can do that. The script for that, by the way, looks like this, and it's also going to be in the directory. This isn't creating hdd.img, it's creating harddrive.img. But you can see I just have to install one tool, and then these 2 things create this file. But this is just basically a bunch of zeros. It's an empty hard drive file. Anyway, so then I want to tell it that I don't want it to open a window. I want it to... This means the same thing as the earlier command. I guess I forgot I wrote that. But it means the same thing. Next, I want to have internet. I want to have a NIC. And I forgot what that did. It does something. I am shooting from the hip here, so please forgive me. Now, we're not going to run the build script because it takes like 30 minutes to run. I mean, I have to especially with my internet, I have to download all these GitHub repos and then build everything, and it takes forever. I've already done this before the video was filmed. So we're just going to go ahead and run this test.sh, which only runs that last line. And you'll be able to see an example of what the system looks like when it's working. So, here goes nothing. See these messages right here, by the way? Most Linux systems have these turned off. I do not have the quiet argument passed. If I did, you wouldn't see them. If you don't pass that, the Linux kernel is usually very noisy. It lets you know what happens on the system and then what time it happened as well. So we can kind of see a little bit of the initialization script we gave it. I said, welcome to AshDOS. I put the time on the screen. We are only using 13.9 megabytes of RAM. It's extremely small, out of 1.8 or so, or 1.9 that it has access to, right? And then look at that, we have a little shell that opened up. Let's run the clear command. Now, here's my initram file system the way I made it. If you notice, we got a little like init script in there. Let's go to VI, which comes built into Busybox. Take a look. Look familiar? That's right. This was created using our little script that we wrote. Let's navigate into the bin folder. Now, if you look closely, you'll see a lot of binaries, but Busybox is the only one in green. That's because these are all links to the Busybox binary. Let's go back up. Let's go into lib. If you notice that we've got libc.so.6 or whatever, this is your C library. It's a library file. That has to exist in this folder and be visible for programs that link against this file to be able to use the C library. I'm trying to think if there's anything else interesting. Let's go to etc. Okay, you know what? Why not? This is the DNS that we set up. But as you can see, and in theory, this bash script doesn't have to be how you run, how you create a Linux distro. You can run these one by one. And if you want to, inside your initram file system folder that you created, that you're working through, in theory, you can put whatever file you want. I mean, you can just like dump photos, music, whatever you want in order to, that you know, is part of the initialization process. And it'll just be there. All you have to do is run this section to rebuild the img file. But before you do that, just be aware, you usually have to have more than twice as much RAM, as is the size of your initram setup for your computer to even boot. Otherwise, your kernel will panic. So if you add a bunch of files to that, and then all of a sudden your kernel is panicking, I recommend adding RAM. That will solve that problem pretty quickly. So, what else are we going to do? Well, unfortunately, my QEMU setup doesn't have internet. But that's okay, because I made a Docker image. Power off, force. There we go. And we're going to run that here. Voila. You notice this is just about the same. I've made some tweaks to this Docker image. It's got a couple of extra programs and stuff in it. But nothing that would change the way that it works. What I'm going to show you should work on the other system just fine, especially if you have put it onto a thumb drive and you are, connected to the internet through Ethernet or something. Anyway, so let's create a folder here, and I'm going to call it temp as opposed to TMP. I say that, and then I go into TMP. Let's go to temp, right? I got nothing in the folder. Okay, so remember how I mentioned that this system has package built in through Busybox. Well, what's kind of fun is you can see that we have the glibc installed, as I told it, essentially, in the status file. Well, we could do something kind of fun. Let's go back to here. This is the packages.debian.org. You are able to download all sorts of different packages from here as raw files, and it'll tell you what it's dependent on. You notice that, let me see, libexpat1 is reliant on libc6 and libgccs1. Both of these should be installed as part of as part of the C standard library. So what we're going to do is we're going to go here, and I'm going to open this in a new tab, and we got lots and lots of different things here. Let's download from this link. Let's copy link address, wget, and we're going to be downloading this .deb file. We're going to take a look real quick. We have libexpat1 underscore 2.5.0. Let's install it. So go here, and we're set up. So now we have two packages installed, libexpat1 and libc6. Now, this is the part I was really, really excited to show y'all. I think you're going to like it. We're going to go down this list real quick, and I'm going to show you what all you need in order to set up Python on our little system. So, let's go back here. We're going to download libssl3. Another site that I really like to go to is pkgs.org. You can find, really honestly, for most Linux distributions, the .deb file you're looking for. They will occasionally ask you for a CAPTCHA, but it's really easy. It's really easy, and y'all aren't robots, so you should be able to do fine. Let's go here. So only requires libc6, yay. And look at that, we got a URL. So let's copy this URL real quick, and wget. All right, so there we have it. We have all 5 of these packages installed, and we're going to go ahead and install them in order. So I already got lib expat1. Let's go ahead and install the SSL package and zlib. libpython 3.1 minimal. And then finally dpackage I. That's the big one. Okay, so this is how we're going to resolve that issue, just because the post install script isn't working correctly. What we can do is we can run the dpackage deb command, tacx, python, 3 minimal whatever, python temp. There we go. And we go into the python temp directory. And every Debian file, or every .deb file, is essentially like a zipped or compressed version of the file system Delta. It includes all the folders that it needs to copy files to, and then what they look like on the inside. So USR is actually a folder we have at our top level directory. So in order to install a Debian file without using the tool or running the post install script, what we want to do is we want to do cpr USR, or actually we'll just do this. What this is doing is it's taking everything within this folder and copying it to the parent directory. So we do that, and now if we go to the parent directory and we clear and we go into USR, and we go into bin, we have Python. Now, another problem is that this is having trouble finding the C library. Because we couldn't run the post install script. But there's actually a simple solution to this as well. Okay, sorry about that. I had to go on a little bit of a rabbit hole there for a second. So the problem from earlier is that I needed to copy my library files from this folder into /lib64. I could not create system links. I had to physically copy them with the cp command. But once that's done, check it out. Oh, don't check that out. It's not on my system path yet. I have Python 3.11 running on this tiny system. So I can do like for I in range 10, not that, 10, print I. And when you look at that, Python is actually working. There is no pip or pip install, it's just Python. But you get the idea. Like, that's how you can install actual functioning Linux programs on this tiny little Linux system we put together. Now, we have exhausted ourselves thoroughly by going through this entire process. Why don't we do something else and take our little system we put together and put it on a disk? That's what the create_iso.sh script is for. Fortunately, most of these packages you don't have to download from GitHub or anything. You don't have to build them. You can just download them from apt and then copy their binaries onto the disk. It's super easy. So that's what we're doing here. We're going to be downloading these libraries, and then what we're going to do after that is we're going to make a directory. We're going to actually make a couple of nested directories. ISO is where our ISO is going to sit. And then from there, that's going to also be the file system we eventually bake into this thing. So we're going to create a boot folder and then an ISO Linux folder. First thing we do is we copy our kernel file, which is located deep down in this folder here. So what we then do is we take the initram file system.img and we put it into the boot folder as well. So you see we're kind of getting a system set up. Finally, what we're going to do is we're going to take a bunch of these binaries and boot menu configuration files and place them into the appropriate places for syslinux to work. And I don't know if these look familiar to you. They certainly look familiar to me. but this is going to be the configuration file that stores the arguments we're going to be passing to the Linux kernel. So I'm going to let it know that this is, what my kernel is. This is where I want the, I'm trying to say the init RAM file system to be. Finally, make isofs takes our file system, or at least our folder that we created, and then creates a .iso file, calling it ashdots.iso. I'm going to let it know that's where the ISO Linux binary is. And here's where the catalog menu file is. I'm letting it know to set up a boot table. The CD itself is going to be named ashdos. And then this is optional. You can comment this out if you want to explore the files afterwards. But what this does is this creates, or at least it gets rid of all of the temporary, cache files we set up. So from here, what you want to do is you want to take your ISO file you've generated and you want to put it onto either a thumb drive or a CD. With a CD, it's very easy. ISO is designed to be burned directly to a CD. You should have system processes for that. If it's a thumb drive, I recommend Balena Etcher on Linux and Mac, and I recommend Rufus on Windows. That's my poison. That's my tool of choice. And then what that will do is it'll create a bootable disk that you can then plug into an x86-based computer, as long as it's 64-bit, which most modern computers, they will be. And you boot from it. And it just straight up works. Here's an image from when I booted into the system on a little Lenovo all-in-one PC that I set up. You can see me trying to connect to the internet and doing other things. Anyway, this has been a very long video, but I really hope that this has been very useful in teaching you sort of how Linux works at a very low level and how to build, or at least to create a starting off point for your own minimalist Linux distro. There's a lot of things that this isn't doing. It's not mounting any hard drives. It's not connecting to the internet. But you can do both of those things. You can mount hard drives connected to the internet with this without too many issues. You just might need to customize your initialization script. It also doesn't have any schedulers. There's no cron, there's no systemd. It won't start anything unless you tell it to start. And there's no graphics. In order to get graphics set up on a system like this, you'd have to install over 100 packages. I spent 2 hours the other day trying to find all the packages that I would need to get this thing set up. It's crazy. And obviously you don't have a package manager. You have to manually do that yourself. But aside from that, this is all you would need to build a Linux system. You can, in fact, install this onto a computer and, in theory, build all the way up to a modern Linux desktop without having to build anything else into it. So this is a tutorial for something that I personally have been wanting for a long time, and I really hope that y'all get a lot of interesting and useful information out of it. Please leave comments down below if anything doesn't work for you. If you see any tweaks to the GitHub script, that's probably why I probably went back and fixed some things. But with that said, thank y'all very much. I really appreciate all of y'all. I'll probably see you again with a completely different room layout in 6 months. I don't know. I'm keeping myself busy. I've got a lot on my plate. This channel is definitely not a priority. It's a side project. But regardless, it is really fun. So I hope y'all have a great day. Peace.